In this video, we discuss bifurcations. A bifurcation value is a value for a parameter that causes the system to qualitatively change its behavior. To gain fixed points or to lose fixed points, or for existing fixed points to change their stability. We'll investigate this via example, and keeping with previous videos, we'll select an example from population dynamics. Let's consider the population model dp dt equals AP minus BP squared minus H. This looks a lot like the logistic model, except that we have this H term. This H is a harvesting term. The population is growing logistically, except that we're removing animals from the population at a fixed rate. The classic example of this would be fish. The fish population in a bay might grow logistically, but fishing industries harvest fish for commercial use. Here, A and B are constant parameters representing birth and death rates. We can't change those, but H is effectively a variable. We can increase or decrease the number of fish we harvest. Let's analyze this differential equation in terms of its fixed points. First, let's observe that dp dt equals negative b p squared plus AP minus H is quadratic. It can have 0, 1, or 2 fixed points, depending on the discriminant, which in this case is A squared minus 4BH. Remember that the discriminant appears under the square root in the quadratic formula. If it's negative, there are no real roots. If it's 0, there's 1. If it's positive, there's 2. If H is large enough, this discriminant is negative, and there are no real fixed points. That is to say, this quadratic has no roots, and of course, the fixed point of this differential equation are precisely the roots of this quadratic. In particular, large enough means H is greater than a squared divided by 4b. Then this is negative. The derivative is never 0, and there are no fixed points. If we draw the phase diagram as the x-axis, as we did in an earlier video, this will be easier to visualize. Here's the x-axis. The derivative looks like this. It opens downwards because of this negative term. And the only way for a quadratic that opens downwards to never intersect the axis is for it to be totally under the x-axis. Since the derivative is always negative, population is always decreasing. As a side note, this model includes a bit of unreality because this harvesting is not tied to the current population. The model claims we can keep harvesting after the fish go extinct, and population equals 0 is not a fixed point. This doesn't bother us. We can apply a little common sense to our mathematics. The harvesting term controls the vertical shift of this parabola. We don't want the fish to go extinct, so we start to reduce harvesting. That pulls the parabola up. And when h equals a squared divided by 4b, the vertex of the derivative now touches the x-axis. Well, the derivative is 0 here, so we now have a fixed point, but the derivative is negative everywhere else. And you can see the fixed point is unstable. If a disease hits or anything happens that brings this population down a little, extinction will occur. That's not good. So we reduce h even further. The parabola gets pulled up further. And now 2 fixed points appear. This fixed point is unstable, but this fixed point is asymptotically stable, and the fish population is now sustainable. It will remain near here. If random perturbations take it off this fixed point, the asymptotic stability will pull it back. So h equals a squared divided by 4b is a bifurcation value. That is to say, it's a cutoff point where fixed points are created, destroyed, or change stability. Above this value, there are no fixed points. At it, there's one. Below it, there are two. Intuitively, you might think that having bifurcation values is a bad thing. Didn't we just say in our structural stability video that we don't want minor changes in parameters to radically alter the system? However, the differential equation we just looked at is structurally stable. The secret to that is that, for intents and purposes, h is a variable, not a parameter. Suppose that we alter our parameters slightly. This a changes a little, this b changes a little. Then this bifurcation value changes a little. But the basic behavior of the system doesn't change. We have a bifurcation value. Above that value, no fixed points occur. At it, one unstable fixed point appears. Below it, two fixed points, one unstable, the other asymptotically stable. It is unlikely that we will have much more to say about bifurcations, which is a shame. They're a major topic of interest in differential equations. But the trade-off involved in touching on all the essential material is that sometimes interesting topics do not get the attention they are perhaps due.